Lecture 13a, Lie derivative and Killing vectors. Definition. A Killing vector field capital X on a Riemannian manifold Mg is a vector field that generates an isometry of the metric G. That is, the Lie derivative of the metric tensor G along X vanish. That's a definition how we will obtain in this case the Killing vector equations. Just you set Lxg is equal to 0. This is the Lie derivative. That's a special Lie derivative. This condition says that the metric remains unchanged when you flow along vector field X. That is, distance and angles remains unchanged when you flow, okay, over on this case, okay, of the field. Then angles are preserved, distance and angle are preserved in the direction of X. These flows are infinitesimal isometries. You see, that's what we call isometries. Now, why is it important in intrinsic geometry? As we said before, intrinsic geometry studies the properties of a manifold that depend only on the metric G, not on how manifold is embedded in higher dimensional space. You see, that's important to distinguish between intrinsic geometry and extrinsic geometry. Intrinsic geometry, there is no dot product, no derivation, no cross product, mixed product, you see, and so on. Now, a Killing vector field is important because symmetries, if X is a Killing vector, it generates symmetries under which geometry, that is, distance and angles, is invariant. Second, classification. The number of linear independent Killing vectors constrains the manifold geometry. That is, maximally, symmetry, space have the largest possible number of Killing vectors. You see, this classification over here, we will see when we will present numerical examples about the sphere, this flat space, and so on. Now, the derivation of the Killing equation on the manifold, two-dimensional manifold, it could be extended to any dimension. So this you see in the next lecture 13b. The equations L, the Lie derivative of X of Gij are 0. Gij are the components of a second order tensor. That's it.